In this video, I'm going to be working through how we can determine total resistance when we are looking at resistors in series and in parallel, and to give a problem that we can work through that's going to help us remember some of these core concepts. We're going to be looking at this circuit I've drawn to the left here, and our goal is to find what current is passing through our 6 ohm resistor. And so the very first thing I like to do when approaching these kinds of problems, when we have multiple resistors and multiple resistor setups, in this case we have both a parallel and series setup, is beginning to condense down this problem. And so we can think of this part of our circuit as one resistor. And this one resistor will have a value of Req. And so the formula that you're going to need to remember when you are determining total resistance, when you have resistors in parallel like we do here, is that 1 over Req is equal to 1 over R1, which I will let R1 equal the 3 ohm resistor, and 1 over R2, which in this case would simply be the 6 ohm resistor. And so what we're going to find here is that we have 1/3, which is equivalent to 2/6 plus 1/6 equals 3/6 equals 1/2. So this has a total resistance of 1 over 1/2. So Req is equal to 2 ohms. And so because we now know that Req is equal to 2 ohms, I can redraw this circuit as the following. So we have the 4 ohm resistor we had previously, and now we have this fictitious equivalent resistance of 2 ohms, and we still have our 6-volt battery in our circuit. And why did we do this? Well, we did this because now that we have gotten this circuit looking like this, we can look at resistors in series, and resistors in series, we can think of this as R tot, the total resistance. And in this case, R total is simply the sum of all your resistors in series. So in this case, R total is equal to 4 plus 2, which is going to be equal to 6 ohms. And now that we have the total resistance for our circuit, as well as this total voltage right here, what we can do is determine what is the current. And so we're going to turn to Ohm's law, which tells us that voltage, V, is equivalent to current I times the resistance R. And in this case, what we want to do is find what the current is in our circuit. So we have I is equal to V divided by R, which is equal to 6 volts over 6 ohms, which is equal to 1 amp. Okay, and so now that we know what the total current is flowing in our circuit, the next thing is going to be determining what is the voltage and current and resistance at each point along our circuit. And so this is where it pays to remember some intuition here. And so when we have resistors in series, it is very important to remember that the current will remain the same throughout the entire circuit. So in this case, we're going to have in this bottom diagram here that I've drawn, we're going to have 1 amp running through this entire circuit at every point along this circuit. So we're going to have 1 amp here, 1 amp here, 1 amp here. No matter where you are, no matter how many resistors you've gone by, there's still going to be 1 amp of current. What does change is the voltage drop across each one of these resistors. And so the voltage drop, if we were to move around our circuit and kind of visualize what's going on here, is that we have 1 amp moving through our 2 ohm resistor, and again turning to Ohm's law, V equals IR, we will note how voltage will be equal to I, which is 1 amp, times R, which is 2 ohms. Therefore, if I was to put a multimeter on this circuit, I would measure a voltage potential of 2 volts on both sides of this resistor. And we can repeat the same process for the 4 ohm resistor. And what we would see is that because the 4 ohm resistor has 1 amp running through it, we're going to be realizing a 4 volt drop across that resistor. And what you're going to note here is how by the time you get back to your 6 volt battery, you have used up 6 volts of potential, which should agree with your initial total assessment for these terms. And that is another sanity check you can do in these types of problems. And so basically what I've now said is that if we were to look at the circuit that we simplified earlier, in which we had the 3 ohm resistor and the 6 ohm resistor. So here's our 3 ohm, here's our 6 ohm. What we know is that there is 1 amp of current coming in, 1 amp of current coming out, and we also know that the voltage drop here is 2 volts. Now, because we're working now with resistors in series, we can no longer say that the current at this point is the same as the current at that point. What we can say, however, is that because the wire is the same on both of these resistors, because they're connected to the same wire, and we are assuming no internal resistance in our cables, what that allows us to claim is that the voltage on this cable, the cable holding the 3 ohm resistor, is equivalent to the voltage holding the 6 ohm resistor. And so if I wanted to determine the current on the 3 ohm resistor, I could do so following Ohm's law again. So we had V equals IR, and in this case we want to know I, so we solve for I is equal to V over R. We know that voltage had to be 2 because of that intuition we have that the wire has to have the same voltage drop across or has to have the same voltage over that entire wire. And the resistance here is R, that is 3 ohms. So we have 2/3 amps running through our 3 ohm resistor. And now if we repeat the process looking at our 6 ohm resistor, we find here is that we look at voltage over resistance. This voltage was equal to 2 volts and our resistance was equal to 6 ohms. This tells us that we have 1/3 amps running through our 6 ohm resistor. And again, I would like to emphasize more intuition at this point. If you think of the electrons as water flowing through something, and we think of these resistors as beds of rocks, we can kind of think of this as the 6 ohm resistor having twice the number of rocks in the way impeding the flow of water. So intuitively, the water will flow the path of least resistance. And what we see here is that we have double the amount of water, double the amount of electrons flowing through our path of least resistance, which in this case is that 3 ohm resistor. And in addition to that, if we say that electrons are conserved in this circuit, we have 1 amp of electrons flowing in from the left. We have 1 amp of electrons flowing out to the right. And what we also see is that we get 1 amp summed up when we sum the 3 and 6 ohm resistors respectively. And so using these methods of intuition and our knowledge of resistors in series and parallel, we were able to determine that this 6 ohm resistor has a current of 1/3 amps moving through it. And again, I would like to reiterate that the reason the current is not the same for these resistors when we're working with resistors in parallel is because the water has paths it can choose to take now, and if there's more resistance for one path, water is going to avoid it and try to go the path of the least resistance, which in this case was our 3 ohm resistor. And so we see how the 3 ohm resistor is being favored in this example. And so I hope you guys find this useful, and thanks for watching.